Today, we are presenting WebSpec, our framework for the formal analysis of browser security mechanisms, and in particular for the analysis of the composition of these security mechanisms. This is a joint work with Benjamin Farinier, Mauro Tempesta, Squarcina, and Matteo Maffei. So it's probably not a news to anyone that browsers are among the most complex software that we use every day. And this complexity is constantly increasing, driven by the addition of new components to the web platform, new components and new security mechanisms. These components are tested by means of an extensive cross-browser testing suite called Web Platform Tests, but they are tested only for compliance by this suite. This suite includes a very large collection of tests. For example, the CSP contains around 4,000 tests. The problem is that web specifications are only reviewed manually by experts and by discussion within the community. And this manual process may overlook logical flaws in the specifications for two main reasons. First, specifications are written in an informal way by mixing natural language and some slightly more structured algorithms. Secondly, these components are mostly evaluated in isolation without considering their interplay or how they compose. So, for example, if we don't know, or we don't have a way to know if when we add a new component to the web platform, the security properties that we expect to hold for the web platforms continue to hold after the addition of this new mechanism. We call these web properties web invariants. So we propose that web platform components and their interaction undergo formal security analysis. How do we do that? In this work, we present WebSpec framework, a framework for the formal analysis of browser security mechanisms that allow the automated discovery of logical flaws and machine check security proofs. WebSpec includes a formal model of the web browser written in the code-proof assistant. This formal model is composed on a set of core platform components and includes recently introduced ones, for example, trusted types and service worker. I want to note that this model is, to date, the most comprehensive one that allows for automated and machine checks proofs. On this model, we define 10 of the web invariants I mentioned before on cookies, CSP, SOP, and CORS. WebSpec includes a lot of automation in terms of a toolchain that allow us to compile the model and our invariant to constrained or clauses for model checking with the Z3 proof assistant. With the Z3 Tiro improver. When Z3 finds a counterexample, the counterexample is minimal by the algorithm that is used within Z3. And with this minimal trace that is composed of browser actions or of events that map one-to-one to the browser actions, we can display an attack trace in a human-readable form, since these browser actions are the minimal ones that allow to violate the invariants. Not only that, WebSpec includes a verifier, a component that allows us to compile the counterexample to an executable test that can be validated across all major browsers. I want now to give you a bit more detail on the pipeline, and I want to start with the definition of web invariants, which again are the properties that we expect to hold on the web platform. And of this, you can see right away that 5 do indeed hold; they are valid. So, and these properties, as I said, cover cookies, CSP, origin header, and the SOP. However, 5 of the invariants do not hold, and of these 5. WebSpec was able to rediscover known attacks, but to discover 2 new ones. One is a new inconsistency between the CSP and a planned modification to the HTML standard, in particular related to the policy container modification and the inheritance behavior of the CSP. The second attack, which will be the focus of the rest of the presentation, is a new attack on host cookies that is caused by the interaction with the legacy API of domain relaxation, the document domain property, that allows to break the integrity that should be guaranteed by the host prefix.
Let's now go through the WebSpec pipeline through an example, namely the invariant on the integrity of host prefix cookies. First of all, what are host prefix cookies? These are cookies whose name starts with a double underscore host, and these cookies are host only, meaning that only the host where they are registered is able to modify them, but not subdomains. Based on this property, we define the following invariant. A host cookie set for the domain D can be set either by D via HTTP headers or by scripts included by pages on D. Next in the pipeline, we precisely define this invariant in the Coq Proof Assistant for each reachable browser state, reachable being the main relation in our model. If there is a script in the DOM running in a given browsing context, and this script is currently setting a host prefix cookie using the document.cookie API, then the domain in which the cookie has been registered must be the domain in which the script is being executed. We can use this invariant for machine-checked proofs, but however, if this invariant doesn't hold, we would also like to find counterexamples. So we write a query based on this invariant and compile it alongside our model to an SMT-lib query. More specifically, the WebSpec compiler translates our query, reachable, and all inductive types of kind and prop into horn clauses. We can now run this query with Z3 and obtain a counterexample. Additionally, WebSpec also produces a sequence diagram that you can use to visually better understand the attack trace. On the right, you can see the example of the sequence diagram we get from WebSpec for this specific attack. In this trace, first, a page is loaded in the top-level window from a.site1.tld. This page contains an iframe, which is loaded from b.site1.tld. The loading of a page is encoded as a pair of event requests and event response, followed by a DOM update, which is parameterized by the DOM element being updated. In blue, highlighted in blue, are the origins that are involved in this trace, which are same site. And this includes the top-level window and the iframe. Next up, two scripts are loaded, respectively from c.site1.tld for the top-level window and from a.site2.tld in the iframe. These scripts then perform domain relaxation by using the document.domain property, by setting the document.domain property to the same value, in this case site1.tld, which makes these two pages effectively same origin. Note that this is only possible since these two pages are also the same site. And finally, the script inside the iframe uses the document.cookie setter of the parent window to set a host prefixed cookie. And at this point, we set a host prefix cookie across subdomains, which violates our invariant. Okay, so now we have an attack trace in our model, but how does this translate to the real world? Is this attack possible in a real browser? With our verifier, we generate an executable test that can be executed cross-browser. The verifier translates each event in the trace to a pair of action and verification. Each action evolves the browser state to match the model state throughout the attack trace, and each verification makes sure that this transition happens as we expect. Not all actions must be explicitly verified, like, for example, network requests or JavaScript API calls. These must be explicitly verified, and this is done using assertions. At the end of the execution of the test, if all assertions succeed, then the attack trace is valid, and we successfully violated the invariant in the browser. In this example, our test includes the top-level loads in the top-level page, a page with two, that includes an iframe and a script. The browser implicitly loads these resources, and we assert that these requests are made successfully. Then the two scripts will perform a domain relaxation for each API call. We generate an assertion that checks that the document.domain property in this case was set successfully. And finally, the script inside the iframe sets the host prefix cookie on the top level. And if this last assertion succeeds, then we successfully violated the invariant in the browser. There are many more components to our work that we could not cover in this talk, like, for example, the compiler, a discussion on performance and scalability and optimizations, machine check proofs, and the additional web environments we mentioned before, and all the supported features that are present in our model. You can find all of this information in the paper, or feel free to come and talk to us. We would be happy to discuss it with you. Thank you so much for listening, and we are open to questions.
Very much. Questions? Yeah, I wanted to ask, about the compiler and to what extent that was using existing general purpose stuff for trying to shove Coq into SMT, and to what extent it was something that you guys were doing yourself, given the nature of the spec that you were writing.
I would say the implementation, we are not reusing any implementation of any known compiler. Yeah. The implementation is from scratch. The compiler is independent of the actual code we are trying to verify, because we start from a subset of the Coq language, which is basically we don't cover all the dependent types. So you can think of a bit more than polymorphic lambda calculus, a bit less than Coq. And the steps of the compilers, I would say, some are quite standard, like monomorphization, lambda lifting, etc. But the main point of the compiler is that its purpose is to find to solve the inhabitant problem, so to find the inhabitants of inductive types. In fact, our queries are defined as inductive types, and our compiler translates this inductive type and the relation to find an inhabitant of it. I would say this will be the main novelty of this compiler compared to other tools like SMT Coq or Coq-Hammer, which are similar automation tools.
Awesome. Thanks.
So I had a question about, you said you're modeling CSP, right? That implies that you understand the spec. Congrats on that one. But that is inherently complex with fallback rules and inheritance and I don't know what, right? So can you talk a little bit about the process of taking this gigantic document which also changes frequently, to actually build a formal model?
Yes, I would say it is a manual process. We don't claim to do any automation in it because it will be impossible, and it's actually, I cannot say impossible because it's actually what the things we are trying to work on for the follow-up work after WebSpec. The point is, it's implementation effort, in the sense that we are doing the same effort that a browser implementer will need to do, reading the specification and implement in a language which is still a specification language, the same, or the behavior we read from the specification. Also, we don't claim to cover the entirety of the CSP spec. We make abstractions, and we may make some implementation details where we cannot use non-determinism to consider all of them. So in general, I would say the process is reading the specification, trying to understand what are the main points, and then implementing it as a transition system in our model.
Cool. Thank you very much.
Great. Thanks very much, Lorenzo and Pedro.